Video 2.5. Yeah, I'm sneaking in a video here between videos 2 and 3, so this will be considered video 2.5. We're going to look at the general addition rule like we did in video 2, but a little bit more in depth with some scenarios that could happen. So first off, our basic probability rules that any probability is between and including 0 and 1, or 0% and 100%, that the sum of our sample space of all of our probabilities that could happen must make 100%, that the complement of any event is just equal to 1 minus the probability that that event happens. So if we want to find a probability that an event does not happen, 1 minus the probability that it does happen. And the last one involved for disjoint events or mutually exclusive events, that there is no overlap between events A and B. If we wanted to know the probability that A or B happens, then we just add together those two separate events. So if we had a two-way table, and we've looked at this example in many videos before, especially in chapter 1, let's talk about some basic probabilities here and see where this is going to be different than video 2. So the first question says, what is the probability of selecting a 25 to 34-year-old? Well, to remind you, this problem, again, we had 4 different levels of education and 3 different age groups. And altogether, we had 175,230 individuals. So the probability of selecting a 25 to 34-year-old, and this is pretty much saying regardless of their educational status. Well, we have a grand total of 37,786 25 to 34-year-old people out of our grand total of 175,230. So the probability is 37,786 out of 175,230. And whatever that is as a percent, you could write that, but I'm just going to leave it the way it is right here. And that could simplify, but really I don't care, just as long as you get how I got that probability. The second problem says, what is the probability of selecting a high school graduate? Well, how many high school graduates do I have? And when we're talking about high school graduates, we mean that's the only thing that they achieved. They did not go beyond that. So we know they completed high school. We have 58,087 of those people out of, again, a grand total of 175,230. So there's our probability there. But now when we start combining probabilities like we did before, but there's an issue in this next one. So it says, what is the probability of selecting a 25 to 34-year-old or a high school graduate? Well, our 37,786 people really was a combination of these 4 groups of people, right? If we added all those together, we'd get our 37,786. Now, if we want to also include high school graduate people, these are all the people that were high school graduates among our different age groups. Now, these 2 events, 25 to 34-year-olds and high school graduates, those are not disjoint events because there is some overlapping here. We could be talking about 25 to 34-year-olds who are also high school graduates. If we were to add together all these people, if we were to say, hey, let's just take all these people plus all these people, there would be some of those people in this summation that we would have included twice. And who did we include twice? Well, these 11,546 people, they were a part of this 37,786, and they're also a part of this 58,087. So if we've included them twice technically, we need to subtract them out one time to make up for it. So anytime probability-wise that we use the term or, we don't mean an exclusive or like we normally do in everyday life. If we say, would you want this or that? And you have to pick this or that. Those are your only 2 choices. But in probability, or also represents the and case, the inclusive case, where we could have both things. Okay? So again, like I mentioned here, or does not mean one or the other, but it includes one or the other or both things combined. So if we wanted to figure out what's the probability of a 25 to 34-year-old or a high school graduate, I really have only 84,327 unique individuals. So again, how did I come about this number? I could add these 2 numbers together, and what does that come out to be real quick? Whoa, wrong button. Calculator, where's my calculator? Calculator. Oh, there it is. We need 37,786 plus 58,000, and that's not typing. That's awesome. All right. 37,786 plus 58,087. Really, we have 95,873 people, but again, we've included those 11,546 people twice. They're in both groups. So if we subtract them away one time, then we should get this 84,327 unique individuals with nobody that's been double counted. All right, so if we have disjoint events, we're going to have to do something about the people that got counted twice that were technically in both groups. Now, our addition rule that we had earlier really only worked for disjoint events, right? Whenever we said the probability of A or B, well, that's equal to the probability of A plus the probability of B. But if A and B are now non-disjoint or not mutually exclusive, we have to talk about a kind of a third part we're going to have to consider, because there could be people that have been both in event A and in event B. All right. So now let's discuss what that's going to look like. So if we had two or more disjoint events, pictorially, if we had a Venn diagram, let's say we have three events A, B, and C, and if they're all disjoint or mutually exclusive, there's zero overlapping going on. But if we have non-disjoint events, and I'll just have two events here, A and B, my two events could overlap, and let's say where they overlap is where both A and B occurs. Now, I could write this a little bit differently. In this region, right in here, this is where A happens, but B does not happen. So I could say this region is A and B complement, not B. And in this little crescent moon over here, this is where B happens and not A complement. In the middle, this is where A and B both happen. On the outside of everything here, this is where not A and not B occur. So there's really four regions here. We got where just A happens, where just B happens, where A and B both happen, and where A and B both do not happen. So when we get disjoint, there's going to be some extra stuff we'll have to consider. Now, the rule that we came up with for disjoint events was if A or B or C were to happen, we could just do their individual probabilities and add them. But again, if we have non-disjoint events or non-mutually exclusive events, we can still do the probability of A plus the probability of B, but then it's going to be these people right in here that have been counted twice because they are both in A and they're both in B. So they've, again, been included twice in this whole ordeal. So what we're going to have to do, and I'll move this over, I'll just shrink it up here, is we can still have the probability of A plus the probability of B, but we'll have to subtract away the group of people that got counted twice, once in A and once in B. So we're going to subtract away the probability that both of those occur. Again, because both of them have already been counted twice. Now, some playing card examples here. If I wanted an ace or a king. Now, ace and king, those are disjoint events. I cannot get the ace of kings or the king of aces. There's no such card. So those are completely disjoint events. So I can look at that as what's the probability of ace plus what's the probability of a king. And both of those have a 4 in 52 chance. And if I add those together, I get 8 out of 52, which simplifies to be 2/13. Now, a non-disjoint or a non-mutually exclusive example using playing cards would be, what if I wanted an ace or a red card? Well, now I got to consider, are there any red aces? And yeah, there are two red aces, the ace of hearts and the ace of diamonds. So whenever I discuss aces, there are 4 aces altogether. And how many red cards are there? There's 26 red cards. Half of the cards of the 52 are red. But then I got to consider, what cards have I counted twice as a part of this 4 and a part of this 26 would be the 2 cards we just mentioned earlier, the ace of hearts and the ace of diamonds. So I need to subtract away 2 out of 52. So once I put all that together, I get 28 out of 52, which simplifies to be 7/13. Now, the one example we're going to look at together says Deborah and Matthew are anxiously awaiting word on whether they have been made partners of their law firm. Deborah guesses that her probability of making partner is 0.7 or 70%, and Matthew's is 0.5 or 50%. These are personal probabilities reflecting Deborah's assessment of chance. So these are just kind of out there. This is what she thinks is happening. Deborah also guesses that the probability that both she and Matthew are made partners is 0.3 or 30%. All right. So that right there, that last statement, that 30% thing is telling us that the events Deborah is made partner and Matt is made partner, they are not disjoint events because they could both be made partners of their law firm. But we also have to consider that, well, maybe neither of them are selected partners of their law firm. All right. So the first thing we're going to do is draw a Venn diagram illustrating event A, Deb is promoted, and that B, Matt is promoted. And again, we just said these events were not disjoint, so we may overlap these events here. And so let's call this Deb's bubble, and this is Matt's bubble. All right? And the overlap here is where Deb and Matt are both made partners. Now, some extra things I can throw in here on these two parts. This is where just Deb is made partner and not Matt, right? So let's call this A and not B, B complement. And likewise over here where Matt gets promoted but not Deb, this would be not Deb, A complement, and B. Or we could say B and A complement. It doesn't really matter what comes first and what comes second. Now there's a fourth area, which is everything on the outside of our bubble. This would be where Deb is not promoted and Matt is not promoted. So there's our Venn diagram, but we also need to list all of the probabilities. And there were three probabilities floating up in this problem, 70%, 50%, and 30%. And if you consider those three probabilities, that adds up to be 150%, which is impossible. So there's a little bit of math we're going to have to do here. So number one, the one probability you want to try to start with is the overlapping part, okay? Because we were told that both of them is 30%. So here's 30%, 0.3. Now, it said Deb has a 70% chance of making partner, but that includes any scenario where she is made partner. Now, that 70%, if we look at our Venn diagram, is all of this bubble. In all of these situations inside this bubble, this is where Deb is made partner. But look, we've already got 30% of it taken care of right here, where she and Matt are made partner. So how much is left over of that 70% where only she gets made partner and Matt does not? Well, that's got to be a leftover 40%. Again, 40 and 30% altogether makes 70%, which we were told, but we've already talked about 30 of the 70% for when they are both. Now, we're going to do the same thing for the 50% for Matt. The 50% means all of this bubble. This is all of Matt being promoted. But we've already talked about 30 of his 50% goes to him and Deb being promoted, which means the probability that purely just Matt gets made partner and Deb does not has got to be the leftover 20% to make that full 50%. Now, how much do we have collectively here? We got 40, 30, and 20%. That makes 90% altogether. So where does the leftover 10% go? Well, that's got to be where neither one of them are made partner. So we're going to take this picture with us to the next page so we can answer some additional problems. All right, let's take that guy, let's shrink it up, and now let's look at problem number 2. It says, write a probability statement and calculate the probability that at least one is promoted. Well, if at least one is promoted, that means Deb got promoted. We could say Deb only, or Matt only got promoted, or both are promoted. Okay, because at least one means one or more. So these would be those three situations. Now, if we're only talking A or B or both, well, really that's the same thing as saying that Deb or Matt are selected. And that was equal to the probability of Deb every situation of Deb plus every situation of Matt, but we said there's some overlap in here. There's really a few different ways we can do this problem, so bear with me here. Oh, not equals. We need to subtract away what they both had in common. So we could take all of Deb's probabilities and all of Matt's probabilities, and right there you know something's fishy because this is 120%. But we've included the 30% where both of them are selected twice. So if we get rid of that 30%, now we're at 90%. Now, a quick and easy way you could have gotten 90% would have been just to say, well, it's this probability plus this probability plus this probability. So if you want to write this out, you could say the probability of A and not B plus the probability of A and B plus the probability of not A and B, and then you could say, well, there's 0.4, 0.3, and 0.2, and you're done. Really a much faster way to do all this, to be honest, the at least one scenario, the probability of at least one is equal to 1 minus the probability that no one is selected, right? And do we know the probability that no one is selected? Yeah, it was at 10% down here. So if I took 1 minus the one situation I don't want to see happen, there's my leftover 90%. And this is probably the fastest way to do it. So anytime you get that at least one scenario, just take 1 minus what you don't want to see happen. Okay, use the complement rule, if you will. All right, problem 3. Write a probability statement and calculate the probability that neither of them is promoted. Well, the probability statement would be the probability of A complement and B complement, right? That's not Deb and not Matt. That's neither one of them. And we already know what that answer is. It's 0.1 based on our Venn diagram. Now, I will tell you up front that getting the probabilities is really easy most of the time if you already have all the probabilities figured out in a Venn diagram. Sometimes it's not so easy to figure them out in the Venn diagram. Sometimes drawing a Venn diagram is impossible for a scenario. So I'm not saying it's always going to be easy, but it does take a lot of the work out. Oh, this thing's being crazy now. Don't want that. Come on. All right, let's finish our last problem here. Write a probability statement and calculate the probability that Matt or Deb is promoted. Well, that's really what we've already done in problem 2, right? The probability that Matt, or that's not Matt, Matt is B, so really we're saying B or A, but that is again equal to the probability of B plus the probability of A, but we got to consider any overlap of A and B. And so again, we're going to get the same answer we had for number 2, right? B, Matt, has a 50%, Deb was at 70%, but we got to subtract away their 30% overlap. And once again, we get our 90%. Okay, so at least one and Matt or Deb, that scenario, both of those were the same thing. And that is it for video 2.5. We'll see you next time for video 3.